Thank you for taking the time to listen to the result of the past 3.5 years of my work with Professor Chikmisha and some really incredible collaborators on the topic of using convex optimization in a non-convex world. We'll unpack those statements in a little while, but there are some exciting applications to aerospace systems. So I'd like to begin with a brief history of control. If such a thing is possible, I won't dwell on this too long. Control began a long time ago, and it began with clocks, unsurprisingly. Water clocks, pendulum clocks, even natural selection and evolution theory touched them. And then control for a long time, from the 1700s onwards, was all about controlling steam engines with mechanical governors. So it was all about speed regulation of some of the earliest engines of the Industrial Revolution, after which we realized that we can build bigger ships, bigger machines that our muscles can no longer operate, and control helped us to move large things like the keels of much bigger ships. And that was the topic of servo motors from the 1800s onwards. And then in the early 1900s came the advent of the telephone and the electronic amplifier. And that's where the Bell telephone labs that we all famously know in the control community came in. And a lot of work happened in telecommunications, where in some sense modern control theory grew up. In the second half of the 20th century came the computer. And one of the earliest complex computers that were also portable that were developed were actually for spaceflight. It was the Apollo guidance computer that got people to the moon for the first time in history. Shortly after the trips to the moon, there came the CPU by Intel, and shortly after MEMS, or micro electronic machinery technology. And now we have an abundance of compute power, an abundance of information. And I would say the topic of control engineering today, in large part, is all about processing information and figuring out how do we make decisions in the presence of an abundance of information. So it's all about information manipulation at this point. So here is a nice diagram for how I'd like to propose thinking about the paradigm shift in control engineering. What we used to do when computers came about is we used to use computers to solve complicated equations. So we kind of knew what to do, and we wrote down the equations for what doing those things mean. And then, because we're just humans, we use these mechanical or electronic machines called computers in order to crunch the numbers for us. The paradigm shift in the 20th century, or shortly before the 20th century, and certainly now, is shifting towards using computers as decision makers. So now, as opposed to knowing what to do, we no longer know what to do. But what we do is we formulate problems. So we define what it is that has to be done, and then we let the computer play the decision-making role. And the computer now has to play a creative task, and that's a very difficult thing to do. It's the topic of optimization that we'll talk about today, but also machine learning, formal methods, all of these theories that are still being actively researched today. So if we narrow down the discussion from solve creative tasks to aerospace guidance, which is the topic in aerospace engineering of generating trajectories for vehicles, then let's talk about what that means. In trajectory generation or aerospace guidance, what you want to do is take some vehicle, be it a rocket or a spacecraft, and you want to transfer it between points in space. Say you want to transfer a rocket from being in flight to being safely on the landing pad. Trajectory generation gives you that plan for how the vehicle should achieve that task. Now, to be clear, plans are imperfect and plans need adjustment. That's where feedback control comes in, and feedback is responsible for, in a way, wrapping around the trajectory and reducing this tracking error, okay? That's an important task if we want to execute trajectories in practice, but I just want to be clear that these are, in some sense, sometimes not, sometimes yes, distinct disciplines of trajectory generation and feedback control, I worked on both for the PhD. I'll mention that briefly, but the topic of this presentation will really be focusing on the trajectory generation aspect. So making plans. So we mentioned aerospace guidance, optimization. Why do we talk about optimization for trajectory generation? Why do we care so much? I'd like to argue that the reason we do is because optimization offers one of the best ways that we know of today to capture some of the constraints that aerospace vehicles need to satisfy when they execute trajectories. A rocket has certain equations of motion, so it can't move anyhow. It has bounds on, for instance, the thrust of the engine. It has pointing angle constraints so that it can't fly, say, horizontally, it must stay around the vertical. And glide slope constraints, which make sure that you approach from above and not from below the ground. All of these words that I said, they all admit neat mathematical expressions in the form of constraints. And the topic of optimization, even beyond just finding optimal solutions, is really about finding solutions that satisfy these constraints. Optimization is a large field. Why do we focus so much on convex optimization? There are 4 key reasons. Convexity is a technical term, but for the purposes of this presentation, because not all of us are familiar with it, I'd like to just boil it down to 4 principal facts that convex optimization buys us. It buys us global optimality, which means that it has the nice property of that when we solve the problem and find some solution that's locally the best, it's actually globally the best. It's the best that we can do. It buys us certificates of infeasibility. What that means is that if an algorithm tells us your rocket can't land given what you gave me, it really means that. It's not that the algorithm didn't find a solution, it's actually found a proof in some way that a rocket will never be able to land under that problem specification. There's polynomial runtime complexity, which is a technical term to say that the problem scales well as you increase the size, and the algorithms can self-initialize. I think this point is not often appreciated enough because general optimization requires the expert engineer to tell them what is roundabout a good solution, and I'll improve that for you. In convex optimization, we can start with a blank slate, which means we don't need to provide any idea of what a solution looks like. The algorithm will find that for us entirely on its own. A very famous and really fundamental professor to the study of convex optimization, actually a professor at the University of Washington, Terry Rockefeller, said this nice quote in the 90s, that the difference between difficult and hard problems is not between linear problems and nonlinear problems, which is kind of the view of the early 20th century. But it is the difference between convexity and non-convexity. So roughly speaking, convex problems are easy, non-convex ones can be pretty hard. Another part of that quote that's, I think, less quoted, but that is actually the most important for this thesis, is that even when problems are not convex, we want to use convexity, or we can use convexity, in order to design iterative schemes that can solve non-convex problems. And that was a giant part of study in my thesis. So, okay, we know that non-convexity is hard. Why do we care about it? Can we approximate things? Can we just avoid it entirely? The problem is that in many cases, non-convexity just cannot be avoided. For instance, a quadrotor, when it's flying through a forest, must avoid trees. This could look like a tree. Obstacle avoidance constraints are non-convex in most cases. So if you want to avoid obstacles, you're non-convex. If your dynamics are like, an airplane and you rotate and translate with fixed engines, your dynamics are nonlinear and are not convex. If you're a spacecraft and you want to rendezvous with a target, your trajectory may have to satisfy if-then kind of logical conditions. Again, that's not convex. So non-convexity finds a lot of presence in aerospace and other applications. So we need to think about it at some point. I'll begin this talk, or the main portion of this talk, with a summary of my contributions over the last 3.5 years. We've been pretty busy publishing several papers, 17 of them at this point, on 4 main avenues of optimization-based control. The first 2 avenues concern model predictive control, where I worked on what are known as robust and explicit model predictive control algorithms. There we wanted to do things like control satellite position around in an orbit, and we wanted to do that robustly with respect to disturbances or computationally as cheaply as possible. The other 2 avenues that I worked on, and these concern really the trajectory generation aspect we were just talking about, are the methodology of lossless convexification and sequential convex programming, or SCP for short. Both of these methods exploit convexity in order to solve problems, hopefully in real time, for things like aerospace vehicles. And it is really this 4th avenue which happened, or where interesting things happened since my general exam. That will be the focus for this talk. So the publications, again, all of these happened since my general exam, that underpin the contents of this presentation are these 3 papers. A survey paper on spaceflight optimization, a comprehensive tutorial on the lossless and successive or sequential convex programming methods, and finally, a novel algorithm for how we can do essentially mixed integer programming without the integers by using sequential convex programming. So we'll talk about all of these. The roadmap for the talk, if it's okay with you, will be as follows. I will first talk about a novel software that I wrote over the past year in the context of this tutorial paper in the middle, that allows us to have a parser-solver interface to solve really general problems with SCP methods. Then I will show how this toolbox can be used for a very simple path planning problem, followed by 2 more complicated examples. A certain starship that you may have seen on amazing YouTube videos in recent months, and the example of Apollo transposition and docking, which is a real maneuver that occurred in 1969, and that we applied our optimization tools on today. So let's begin with this SCP toolbox. What does the SCP toolbox do? Well, it's a generic tool for solving non-convex optimal control problems, which look as follows. So if your problem fits this formulation, you can solve it, roughly speaking, with the SCP toolbox. There is a cost, which is typical for optimal control, contains a terminal cost and a running cost. There are system equations of motion. Next, there are convex path and state path constraints on the state and the input variables. So these are things like thrust bounds. The state has to be, for instance, the velocity has to be no higher than a certain amount. So these are the convex pieces of the constraints. Then there are the non-convex constraints, which are captured by this S equation. And these are really the difficult ones. These are the non-convex constraints that are the name of the game for SCP methods. And finally, there are boundary conditions. And by the way, as we get into more theoretical parts of the talk, I welcome any questions from you, just to course correct in case I lose anybody. Okay, so we have this optimal control problem that we want to solve. We solve it using SCP, which in optimization at large belongs to the family of trust region methods, which boil down to what I think of as an approximation solution loop. What it does is, given your problem, you give it an initial trajectory, and then what it will do is approximate your difficult problem locally around your guess, and then solve that local approximation using convex optimization. So this part is convex. When you solve that, which is easy to do because it's convex optimization. You will test whether that solution is good, in which case you can converge. And if it's not good, then there's a reconfiguration step where the algorithm will decide what to do for the next iteration of this loop. And most typically, that is to refine the space where you trust the approximate model of your problem. So SCP is an instance of a trust region method. So it's actually, this diagram, if it looks complicated, is just an unwrapped version of this high-level block diagram, where the main thing that happens is I reveal what happens in the approximation block. So again, you start with a trajectory guess, and then to approximate your difficult problem, you will linearize all the non-convex parts of the problem first. So that means non-convex constraints get approximated by their first-order Taylor series. Then that linearization may actually introduce difficulties like infeasibility. So we introduce extra ingredients into the problem that we call virtual controls. They're essentially relaxation terms. And then you will also discretize the problem in time. The continuous time dynamics make it a continuous time problem, which has an infinite number of degrees of freedom in how you manipulate the input. That's a problem for computers that generally can't manipulate infinite things. So we need to shrink the problem to a finite dimensional space. We do that through temporal discretization. Once we're done with these steps, we have a convex problem that we solve with a convex optimizer. The advantage of SCP, for instance, for the aerospace community, is that it is agnostic to what this convex optimizer is. So if you have a tool, say, that solves problems like linear programs really well and you trust it, SCP is independent of that tool, so you can use it here. Or you can use another tool. So the algorithm is generic in that sense. Okay, so moving on, I'd like to give intuition for where SCP is positioned in terms of the optimization literature. So really the most fundamental methods in optimization are Newton-type methods for unconstrained and equality-constrained optimization. This being something like minimize some linear function of x subject to, or let me just even say like some convex function of x, subject to a bunch of equality constraints. These are fundamental tools. Interior point methods that have been developed over the past 40, 50 years, they define an iterative scheme that uses equality constraint Newton's method at each step in order to solve the problem. Okay? Sequential convex programming is kind of a natural extension of that idea, in the sense that it can use interior point methods at each step in order to solve a non-convex problem. So it's like the next layer of the cake in this hierarchy. Okay? I think that's a comfortable way to think about this new sort of family of methods. So introducing the SCP toolbox, the big reveal. We wrote this in the context of the Control Systems Magazine paper, and it has grown rapidly since then to outgrow that paper. It's 20,000 lines of code at your command. You can download it at this link, where it provides essentially a parser interface that you can use to define non-convex optimal control problems and solve them using these sequential convex programming algorithms. The algorithms that are implemented in there today, two are from our group, SCVX and the penalized trust region methods, and the Gusto algorithm by our collaborators at Stanford ASL Lab. We also have several temporal discretization methods. The whole code is written in Julia and it's open source, you can download it. We implemented already 8 examples that are in there today that you can get started with. To show the genericness of the tool, it goes all the way from very simple double integrator models of a car, all the way to Starship planar landing flip maneuver, to Mars rocket landing, to spacecraft rendezvous and docking. I think that's a point not to be underestimated, the fact that these SCP algorithms can scale across such a wide variety of problems. So moving on to the second part of the presentation, I will briefly show how you can use the SCP toolbox in order to solve a simple problem, okay, just to motivate how the whole thing works. So Dubin's car is a simple model of like a 2D vehicle that drives on a plane. And the optimal control problem looks as follows. There's a cost to minimize, which is your use of control effort. There are nonlinear dynamics. There's a non-convex circular obstacle constraint that you don't want to drive in. Maybe it's a pedestrian. And there are boundary conditions. So you want to go from here to here, okay, while avoiding the obstacle. In the tool, the SCP toolbox, you will define the problem parameters, initialize the problem. You will set the initial guess, if you recall back to that previous block diagram. In this case, it's a simple straight line from here to the final state. Obviously, it crosses the obstacle. This is one of the powers of sequential convex programming, is that the initial condition, initial guess can be very coarse. You don't need to be an expert necessarily at all in order to find the initial condition that works, or initial guess that works. You define the dynamics. As I said, SCP works in terms of linearization, so you define both the state, time derivative, and its Jacobians. You do the same for the obstacle. All of it, again, it's through this parser interface. And you define the boundary conditions. So far, 72 lines of code written. And then you basically say, pick which of the SCP methods you want, and you hit run. Or in this case, you write solve the problem. 20,000 lines of code do their thing and come up with this trajectory, which is pretty simple. It's the car drives hugging the obstacle. It's, so you could say, okay, you wrote this much code. It's a simple trajectory. What's so interesting? I'd like to remind you of the diagram that I showed at the beginning of the presentation, of that we're talking today about computers performing algorithms that are creative. So computers are decision makers. In some sense, they're creative, starting to be creative thinkers. So something interesting happens with this problem when the obstacle grows. By the way, you can also show the convergence history. So if the obstacle increases in size, something fundamentally different happens about the trajectory. Before, the car just drove straight and avoided the obstacle. Now the car reverses, then drives straight, and then does a reverse parking. None of this was specified to the algorithm beforehand. It decided it by itself, just given the problem definition, dynamics, and such things. So this is like a toy example that we'll see more of in the rest of the presentation, of where the algorithm is, or the optimization is being, in some sense, a creative thinker about how it exploits the model that you give it. So now we'll move on to the next exciting example of the Starship vehicle landing. And just a disclaimer, this is a demonstration of these methods being applicable to this kind of scenario. We didn't work with SpaceX to create this. So the Starship does an interesting maneuver where, after doing a so-called belly flop and falling down like a parachutist, in the last half a kilometer or so, it turns on its engines and has to perform an extremely dynamic maneuver where it flips back upright and lands on the landing pad. It's a 120-ton vehicle doing that in the space of half a kilometer. So it's a very impressive maneuver. We can solve it with the SCP toolbox. We define the equations of motion as before. These are rigid body dynamics in the plane. So it's a 3 degree of freedom vehicle. You define the constraints on things like the gimbal angles and rates, the tilt of the vehicle, and the thrusts. An interesting aspect of this problem is that in the first phase of the flip maneuver, if I illustrate it like this, in the first phase, it uses 3 engines to do the flip, and then it has to switch to 1 engine. At least in some of the past landings, it was the case. So the optimization will actually decide for us when to do this switch from 3 to 1 engine. The cost for the problem is, of course, to minimize fuel, and also for safety reasons, we added a term to encourage the flip to happen as quickly as possible. Okay, so to minimize the loss of altitude while doing the flip. Like I said, it's a two-phase optimization, so the switching time is decided by the optimizer. And here is kind of like the sizes for reference of the sub-problems that are solved in this iterative scheme. So the solution, we hit solve like before, and we find a trajectory that looks pretty similar to what it looks like on the YouTube videos, which is exciting. Here's what it looks like in terms of the history of times. The gimbal angle, gimbal rates, all constraints that we imposed are satisfied. Here's this switch from 3 to 1 engines that happens. And this switch time of 5 seconds is decided by the optimizer. And I did a short test of timing the YouTube videos, and the real Starship does land in roughly the same amount of time as this optimization simple example gives, which is nice to see. Here's the convergence history. The algorithm is really quick at converging for this. Just 5 iterations and you're done. The solution time, because this was not particularly optimized for speed, is dominated by the discretization. In the past work that we've done, we have reason to say that this can be shrunk by like a lot, 10 times or more. So we could argue that SCP can solve the Starship problem in probably less than 1 second. Now we arrive at the fourth and kind of main star of the presentation. This is our paper, recent paper for the AIAA Journal of Guidance, Control, and Dynamics, where we solve a 6 degree of freedom terminal rendezvous problem that has discrete logic elements in it. So if-then statements that typically require integer programming, we don't use integer programming, of course. So the example is motivated by the real NASA Apollo transposition and docking maneuver that happened during each of the Apollo moon missions. The maneuver consisted of the command and service module separating from the third stage of the Saturn vehicle, moving a little bit forward, turning around by 180 degrees, and then closing in and extracting the lunar module to go on its way to the moon. We will show how to use SCP to solve this portion of the trajectory, and actually an even more complicated scenario that nevertheless inspired by this maneuver. So we begin, like we did before, by defining the dynamics. These are simple, rigid body, 6 degree of freedom dynamics that have a correction term for the non-inertial frame, known as the Cohesi-Wilshire dynamics, assuming that the maneuver happens in low Earth orbit. Okay? So the dynamics are pretty simple. The interesting part comes with the thrust model. So the spacecraft is equipped on its circumference with 4 by 4 reaction control system jets. So there are a total of 16 rocket engines, essentially, that are mounted around the circumference and that the spacecraft can use to maneuver in space. The model that we will use for these reaction control thrusters is as follows. In reality, they fire for a fixed, they fire with fixed thrust for a certain time duration that you tell them. So this gives kind of a rectangular pulse signal. Rectangular pulses are totally doable, and we've done it for a SciTech paper from 2020. But they introduce unnecessary complications into the problem, given that these pulses last for really short periods of time, given the multi-minute or hour length of the trajectory for rendezvous. So we simplify them by assuming that they're infinitesimally short pulses that exert the same amount of net impulse on the vehicle. So that basically ends up being that we shrink the pulses to a 0 time duration while increasing artificially the force to maintain a constant impulse. So once we agree on that model, we can define a history of such pulses that occur during the rendezvous maneuver. So what the optimization task is to decide on this history of pulses: when do thrusters fire, when do thrusters not fire. The difficult part about this problem, and actually the original motivation for using this as the example, is what's called the minimum impulse bid constraint, MIB for short. What it says is that reaction control system jets can't fire for infinitesimally small duration of time. There are some fundamental physics or engineering things like downstream propellant flow, residual pressure, that mean that if you can't fire a thruster for as small a duration as you'd like, there's a certain lower bound to that. So you have a decision to make each time that you fire a thruster. Do you fire it not at all, so you keep it silent? Or if you fire it, do you do so for some minimum amount of time? So there's a minimum impulse that gets imparted on your spacecraft. This is represented by a logical OR constraint in the optimization, which means it's a discrete logic constraint that's difficult to handle. Other discrete logic constraints in the problem are the approach cone and the plume impingement constraint. So the approach cone tells you that if the spacecraft is close enough to the target within some radius of r, then it has to stay inside of this cone region that I illustrate here. What this cone does is basically prevent excessive lateral motion of the spacecraft with respect to the docking port of the target, which you don't want when the two things are very close. The other related constraint is plume impingement, which says that similarly, if you're close enough to the target, don't fire your front thrusters because you might actually fry the exterior surface and hurt the thing you're targeting. So both of these constraints, again, are discrete logic constraints. Discrete logic constraints, like I said, are challenging because of this implication statement, which basically encodes, if you're more familiar with, say, programming, if then logic. It says that if this holds, then this must hold. Okay. Traditionally, this kind of logic would be modeled using integer or binary variables. And that's the domain of mixed integer programming, but that's computationally an expensive approach and rarely real time for high dimensional problems. So we want to do something better because ideally it's going to be an onboard algorithm. So let's begin by introducing the kind of general discrete logic constraint that we want to consider. The benefit of generality is that as long as we know that we can model our spacecraft constraints using this template, then we can handle them and we can handle a lot more other optimization problems, right? So this is the template that we define. We begin with this function r, and r is like something that takes values of 0 or 1 representing truth. So when r is 1, then you want these constraints represented by fr to hold. When r is 0, then you go into this else statement where constraints represented by fl must hold. How is r defined? It's defined as an or combination, so this is like a logical or statement, over functions gi, which we call predicates. Okay, it's the term we use for them. What predicates tell us is that whenever one of the predicates is positive, then we want fr to hold. When all the predicates are negative, then fl holds. Okay, so there's this kind of play between the two. Here's an example to illustrate the effect of this discrete logic. So here I illustrate two predicates, G1 and G2, and their sub-level sets, which are the sets of values of Z, which is the optimization variable, the sets of values of Z where G1 is non-positive or G2 is non-positive. When you intersect them, you get this set, And that intersection by De Morgan's theorem actually represents the else statement. And it's easier to explain in illustration this else statement. So when the else statement holds, you want FL to be non-positive, right? So FL and FR actually define their own sublevel sets, which I illustrate here. And what happens when you impose the discrete logic constraint is a set intersection, okay? Where if the else statement holds, which is this set, I illustrated it here as well, then you want FL to be non-positive. So you intersect the two and you get this else set, which is their intersection. You do the reverse process similarly, and you get the if set, which is represented by this. So what the discrete logic did, you can think of it this way, is it basically chopped up these four sets in this case into non-convex disjoint sets where the decision variable has to live. Traditionally, these are non-convex disjoint sets. That rings all the bells of mixed integer and non-convex programming, which as far as spaceflight is concerned, they're great algorithms with great advances made in recent decades, but they're just not implementable on board vehicles. They're too slow, too expensive, generally speaking. So we want to handle this constraint using sequential convex programming. How do we do that? Well, we begin by reformulating this if-else logic into something we can work with. It turns out that this set of two lines of mathematics is equivalent to this constraint. Why is it equivalent? Well, remember, when r is true, it's equal to 1. So when r is equal to 1, then this expression boils down to fr is less than or equal to 0. When r is 0, the reverse happens, and this turns off, this turns on, and FL is less than or equal to 0. So this constraint is an integer constraint, but it is equivalent to what we were talking about before. Now, to use sequential convex programming where we can hope for some real-time performance, we need to make this constraint from an integer constraint to a smooth constraint, or a differentiable, okay, with continuous variables. We do this by replacing R with a smooth approximation of R that I note down by R tilde kappa. So the tilde means, it's generally a different function. Kappa, on the other hand, is what's called a homotopy parameter, which as you increase it, it'll make R tilde kappa converge to R. Okay, so as kappa grows big, this thing essentially becomes indistinguishable from R itself. Here I will show now how this R tilde is computed. We call this like a pipeline for smoothing discrete logic. We begin on the left-hand side with the predicates, which are the GIs, so G1, G2. I illustrate here a simple scenario of one GI being this parabola and the other GI being this linear function. We begin by normalizing them so their values are between 1 and minus 1. That helps to standardize the algorithm across any kinds of discrete logic you want to implement. Once we've done this standardization, we apply a softmax function, which is a log of the sum of exponential functions, in order to do a smooth approximation of the maximum over these predicates. So the maximum is exactly this. The softmax does a smooth approximation of that. Once we have the softmax, we pass it through a sigmoid, which is a function that looks like this. It tends to 0 for negative values and tends to 1 for positive values. And it'll basically, emphasize parts of the softmax that are positive and de-emphasize parts of the softmax that are negative. And then we do a shift, which I won't get into for this talk, but it's an important element when you consider from which side you want to approach the exact constraint using your smooth approximation. But here's a pictorial illustration that shows what happens when you increase kappa. As you increase it, you go from this super coarse approximation of what looks like not discrete logic at all to something that's like a step down followed by a step up function, right? And that's exactly the discrete logic that's defined by these predicates, because remember, the discrete logic is saying that we are 1 when any GI is positive, we are 0 when all the GIs are negative. And in this case, G1 is positive on values that are smaller than -1. G2 is positive on values that are greater than 1. And both of them are negative on the values in between. So that's our discrete logic that we approach eventually using this homotopy, starting from smooth approximations. So now that we know how to smooth things, how do we use that in a penalized stress region method or a sequential convex programming method? What we do is what's called numerical continuation, whose goal is basically to update this kappa term from a small value to very large values until your discrete logic approximations become exact. It's an iterative process, which traditionally would look like something on the left. You will set the value of kappa here, then you will solve the problem in its entirety for that value, find the locally optimal solution, and then update the homotopy parameter again until this approximation of discrete logic is as exact as you want it to be. The novelty of our method for the JDCD paper was to basically fuse the two steps into a single loop, okay? Into a single algorithm, where what you do now instead is you set the homotopy value, and instead of doing a full solution, you will just do one single iteration. Just one iteration. You will get some new reference solution, okay? And then you will test that reference to see how well did you do for this value of kappa. And according to a decision logic, you will decide whether it's a good enough time now in order to update the value of kappa again, okay? And we'll go over what this discrete logic is in the next slide. But I just want to emphasize this fact that we basically do a single update and a single iteration of sequential convex programming at each pass around the loop. So what does this discrete decision logic look like? Let's begin with the update trigger. So what we do is when we obtain a new reference solution from this single iteration, is we look at how much did the cost that we are optimizing decrease by. If it decreased in relative terms by less than this beta trig parameter that the user sets, then we judge that the algorithm is converging to a local optimum. It's somewhere close. And that means that it's a good time to update the homotopy parameter. Okay. If it doesn't, then we don't update it and we keep it the same. So how do we update the homotopy parameter when this trigger tells us to do so? What we do is we use an interpolation condition, which says the following, that the sigmoid that is responsible for this smooth approximation has to pass through this point here, delta 1 minus epsilon. The delta and the epsilon are set by the user, or they're initialized by the user, set by the algorithm. Once these two values are defined, they completely determine what the value of kappa has to be. And for the update, what we do is simply define a geometric progression from the highest value of delta, or highest value of delta, to the lowest value of delta, where the discrete logic is very precise. Okay, so it's basically this process by which delta gets shrunk, and the associated sigmoids become sharper and sharper and sharper. So now let's apply this algorithm for Apollo transposition and docking. We're going to minimize fuel because fuel is always at a premium in spaceflight. And we, like discussed before, impose 3 discrete logic constraints, which are that minimum impulse bit on the thrust, the approach cone, and the plume impingement. And we optimize a more difficult version of these 2 phases of flight, where you do a 180-degree rotation, followed by a rondel. Okay, so what does the trajectory look like? We implemented in the SCP toolbox, hit solve. This is like the user end position trajectory, if you will. It looks very sparse in terms of the thrusts that are used. It is a fuel optimal trajectory. And interestingly enough, the sparsity reminds you of the classical two-impulse rendezvous, right? Where you pulse first at the start and then pulse once at the end. Obviously here it's more complicated due to all the constraints and nonlinear dynamics. You see here that the approach cone is satisfied in that the spacecraft enters this region once it's inside of the sphere. I tested it. If you don't impose this, the trajectory would be somewhere here. So that constraint is important. The next plot I'd like to share is of the thrust pulse history. Here I just show it for 4 of the 16 thrusters, where you see on the left the pulse history kind of in the time view, and here it's in the phase view of this deadband logic where you don't pulse once the pulse duration is smaller than a minimum value. It's 50 milliseconds in this case. The important part that I'd like to point out is that this example demonstrates that we're not getting lucky because the optimization never had to use small thrusts to begin with. Here, in fact, some of the thrusts are very small and almost touch the minimum impulse bit upper bound. So this is showing that the minimum impulse bit constraint is actively being enforced by the optimization. And I tested that if you turn off that constraint, you do actually get, on the region of 5 to 10 thrusts that will linger around in this small area. So that constraint is important. Here is the optimization theoretician's viewpoint, the evolution of the cost function through the algorithm iterations. So our initial guess starts at, a normalized arbitrary cost function value of 3. It's not supposed to mean anything at this point. But it starts out here and pretty quickly converges to a local optimum because the cost doesn't change anymore. But this is for a small value of kappa, so the discrete logic is really not there. When it converges, and see here the change in cost is very small, it passes below our beta trig value and the homotopy value is increased. This causes the cost to jump, to converge quickly again, and the process is repeated until eventually further increases in the homotopy parameter don't really affect the algorithm at all, because it's more or less converged to something that is feasible with respect to the discrete logic. The important part about homotopy is really that to get to this phase, you have to pass through this phase. This phase is where the smooth things are, where gradients tell you things. And the optimization algorithm has time to figure out what it has to do so that by the time you get to the accurate approximations of discrete logic, you've more or less found a good solution. A fascinating thing or property of this algorithm is if you look at what happens when this beta trig, which is this tolerance value right here, is decreased. As it is increased. When you increase it, it means that you tolerate less. You basically are looser and looser in terms of how optimal or locally optimal you want the algorithm to be before you update the homotopy value. So if beta trig is large, like if it's 1, then it means you tolerate really any cost at all, and you will update at the next iteration, the homotopy value. So as the homotopy update tolerance value increases, we want to see what happens to the number of algorithm iterations and also to the fuel consumption of the final trajectory. Normally, what you would expect is that the number of iterations would decrease because you're increasing the homotopy value faster, but the fuel consumption probably will increase too because you're not giving the algorithm time to figure out what's the best thing to do. In our tests for the rendezvous in this example, have shown that across initial conditions, increasing the beta trig value generally decreases the number of iterations dramatically, in this case by over 60%, while the fuel consumption penalty is not perceptible. Like here, it's really absent. There's no trend here. So that's a remarkable thing. Here is an obligatory convergence plot. The algorithm converges in 33 iterations, and it exhibits a superlinear convergence at the end, though we don't have the theory yet to know why that happens, but it is a good property to see. The total solver time is 13.5 seconds. The rest of the time makes it that it's around a 1-minute solution time. Our past experience shows that it would be reasonable to say that we can halve the solver time with a customized implementation and decrease the other time by a considerable amount as well, like 10 times or 5 times if we use a custom implementation, compiled language implementation. So we would expect that a hyper-optimized version of this algorithm could converge in less than 10 seconds, and this keeping in mind that mixed integer programming in past tests really wasn't able to solve this problem in any reasonable amount of time. So the summary of contributions for my PhD, this is one of the closing slides. Before the general exam, I had the pleasure of working on several feedback control laws using model predictive control to do things like robust control and the pre-computation of optimal solutions with applications to satellites and satellite orbital station keeping. I also worked on proving that lossless convexification, which is a method that Dr. Chekmeshi actually developed at JPL about 15 years ago now, but that the ideas of that algorithm can extend to mixed integer optimal control problems, or a class of them at least, that include rocket landing, satellite docking, and we published on those techniques. I also worked on investigating the effects of temporal discretization, something that we mentioned earlier, for the performance of sequential convex programming algorithms, and I developed some early SCP methods for mixed integer programming. Now, since the general exam, 3 things have happened. Me and my co-authors have written a massive survey paper on spaceflight optimization across the board of spacecraft, satellites, planetary and small body landers. And that is getting published in the annual reviews and control in about a week, I assume, because we've received the final copy already from the journal. We also wrote a massive tutorial on the methodologies of lossless convexification and sequential convex programming for the IEEE Controlled Systems magazine, and that is under review. It will be on archive soon, and anybody interested, especially practitioners in these methods, we hope that this becomes an authoritative source to get started on the methods. In the context of this work, I had the chance to develop this SCP toolbox, which is the first of a kind for our lab and other labs to use these sequential convex programming methods like the ones developed by our group in a generic parser solver framework. So I believe it makes them more accessible to newcomers. The last thing was the subject of the Apollo discussion that we just had, which is how to use homotopy and sequential convex programming in order to solve difficult problems that traditionally would require mixed integer programming, but that we're able to solve with algorithms that are potentially real-time capable onboard computationally constrained hardware. The last slide that I have is something that's targeted from the heart to the new students in our lab and in other labs, because I believe, after all, that new students are the generation that will create new advances in these methods. The first advice that I would give, and some of you in the audience will know where some of these advice come from, is decide for your life and work who you want to be and not what you want to be. What I mean by that is chase a lifestyle and not a title. The thing is that you can be the person you want to be today if you do the things that that person does. If, say, you want to become an astronaut, maybe astronauts, read a book every day, or they go work out in the morning. You can do those things today and, in a way, be an astronaut already, even if society doesn't let you become one in the end. The second piece of advice that I would like to give, and that's related, is trust the power of cumulative effort of small actions. If you do something every day to improve yourself relative to how you were that morning, then I guarantee that you will find yourself in amazing places in a month, in a year. So it is a good way to live. The third advice that I would like to give is to find a way to do what you want to do. In life and in research, we are often faced with tasks that, if it's a worthwhile piece of research, probably nobody has ever done that thing before. So nobody can give you exact advice on how to do that new thing you want to do. So you need to find a way to do these things and to trust that these things are possible. Personally, I found that for my research and other things in life, the vision of it happening always came first. And then you have to put in the hard work of realizing that vision, even if others don't see things the way you do. I like this quote by Henry David Thoreau, an American author from the 19th century, which says that what you get by achieving your goals is not as important as what you become by achieving your goals. And I think that's very true in all matters of life, whatever you decide to pursue. So with that, I would like to thank you all very, very much for attending the public portion of my defense. I include here a photo from, I think, exactly 10 years ago of myself building a wind tunnel for a high school science project. What a 10 years it has been since then. It feels like a short time, but at the same time, it's been a long time. I'd like to thank everybody who helped me along the way. In particular, right now, I would like to thank Professor Achikmishe for literally giving me the means and the tools to do what I wanted to do. I can't thank you enough for all that you've given. Thank you very much. And I will take any questions that the audience may have. Thank you.